All right, so what we're going to do now is to discuss how we represent sort of the triangulation on computer and deal with the fact that if you were to, for example, label the vertices in order that there are permutations associated with that and issues along those lines. Okay, so let's look at this whole idea of sort of the ordered triangles. Okay, so of course geometrically a triangle is described by specifying its three vertices. But if you want to represent it as a tuple, it's like of vertices, an ordered tuple of vertices. Then, of course, there are six possible representations of the same triangle, which come, of course, from the permutation of three entries, right? Okay, all right, so let me sort of draw this pictorially for you, okay? So there, in some sense, if you look at these six possible representations, if you think of the ordering as telling you something about the orientation, then those six possible representations decompose into two sets, and each of those two sets represent two possible orientations to the triangles. Okay, so let's look at that. Okay, so let's say we have A, B, C. All right, so if you sort of look at this in lexicographic order, then you'll see that this induces an orientation like this. You go from A to B to C, right? So it goes around in a counterclockwise direction. And there are sort of three ways, of course, it's like to do that by sort of essentially just rotating inside these entries. Okay, so you get you could, for example, get A, B, C this way, and again, it still represents this counterclockwise orientation, if you will, to that triangle. Okay, C, A, B, again counterclockwise. All right, and then in addition to that, of course, they're the ones where the entries are ordered. It's like in a clockwise fashion. So you say A, B, C, right? So this is ordered in a clockwise manner. Okay, you have A, C, B, again ordered in a clockwise fashion. And then you have A, C, B, clockwise. Okay, so now we want to think about how you can get, how you can sort of go between all these possible representations. Okay, so what we're going to do in addition is we're going to label one of these edges as distinguished and having sort of an orientation. So I'll just do that for the bottom edge in all these cases, and all of them are oriented this way. All right, and then this is going to give me a way to also permute the entries. So imagine what's going to happen is that I'm going to have A mapped to B, B mapped to C, and then C mapped to A, right? So if I go from A gets replaced by B, B gets replaced by C, and C gets replaced by A, then this operation maps this orientation or this permutation to this permutation, and we call that the E-next operation. Okay, and the same thing happens here. Okay, B gets mapped to C, C gets mapped to A, and A gets mapped to B. B gets mapped to C, C gets mapped to A gets mapped to B. This moves it this way. Okay, and let's look at the similar thing here. B gets mapped to A. Okay, so that's an A. C gets mapped to B. Okay, so C gets mapped to B, that's a B, and then A gets mapped to C, that's a C. So the operation sort of goes this way here, right? So this is the E-next. I should have said that this operation also goes around this way. Okay, and then here it's like C gets mapped to B, right? C becomes B, B becomes A, and then A becomes C, right? So this goes in this opposite direction here. Okay, so that allows you to sort of these E-next operations preserve the orientation, right? And then so you want to have something which goes between the orientations. And if you look at it, we're going to introduce an operation which basically swaps the order of this bottom part of the edge, okay, which we just call sim. So it's some sort of reflection, if you will. Okay, so these two operations together, right, then allow you to go between different permutations of the vertices. Okay, and so what we're going to do now is we're going to label these 6 vertices in a particular way. So let me sort of, it's a little bit unusual. It's like, but let me sort of explain what's going on. Okay, so I had already said that you know, these 3 represent one orientation and these 3 represent a different orientation. So it's natural to try to encode it's like explicitly it's like that orientation. So what's going to happen is that we're going to represent these 6 possibilities as a 3-digit sort of so a 3-bit it's like number. Okay, so this is represented by sort of 3 bits. Okay, and then with the first bit, it's like represents the orientation. Okay, so so I'm going to write down it's like the binary digits for each of these 6 things, and hopefully you'll see what's going on. So the first one here, corresponding to this, is going to be denoted by 22000. It's like in base 2, which is of course 0, right? In base 10, right? 0, 0, 1. In base 2, it's just 1 in base 10. And then 0, 1, 0 in base 2 is 2 in base 10. Okay, so this corresponds to this corresponds to this corresponds to this. So I'm labeling this 0, 1, 2. Okay, and then for the next row, I'm going to do 1. So 1, 0, 0 in base 2, 1, 0, 1 in base 2, and 1, 1, 0 in base 2. These are, of course, 4 in base 10, 5 in base 10, and 6 in base 10. Okay, so there's this rather sort of unusual representation where you have 0, 1, 2, and 4, 5, 6, right? So we've omitted 3 and 7 in some sense, okay? But that's somehow it's like makes it clearer because it's like now the first digit of this binary sort of digit represents the orientation class, if you will. Okay, so the first bit represents the orientation. Okay. All right, so then once you have that, I can write down what's happening here. So I'm just going to erase this part and write down the expression for eNext as well as sim using the decimal representation. But let me sort of just remind you, maybe I'll just write down here what the numbering is. So this is just 0, this is just 1, this is 2, right? This is 4, this is 5, and this is 6. Okay? All right. Okay. So with that in mind, let's write down what those operations actually look like. Okay. So, so I'm going to output an ordered tree, so ordered triangle, right? And then eNext gives you the triangle and then the orientation. Okay, so this is the triangle and then this is the orientation. And then if this orientation is less than or equal to 2, right, which means it's in this top orientation, then what you want to do is just shift by 1 at modulo 3, right, and return sort of the same triangle but with a different orientation, so which is I plus 1 mod 3. Okay, so that should be fairly clear why that is. Else you return sort of the same triangle again with I plus 1 mod 3 plus 4. Okay, so that might be a bit more mysterious, but let's sort of see what happens when you do this to 4, 5, and 6. Right, so if you do 4, 5, 6, you add 1, right, you get 5, 6, and 7. If you do mod 3, right, you get 2, 0, and 1. And then if you add 4 to it, right, you get 6, 4, and 5, right? So 4 maps to 6, 4 maps to 6, right? 5 maps to 4, and 6 maps to 5. So it actually does work, even though it may not be so obvious. Okay, so that's just to convince you that that's correct. Okay, so that gives you the eNext, and then let's look at what this sim operation does. Okay, so so the sim operation is basically reversing the order at this leading edge, right? So I've labeled this leading edge. So to reverse the leading edge, right, we flip the first bit. Okay, so this again ordered triangle is the output. Okay, and then this is sim operation applied to a triangle with a particular permutation, and you just return that same triangle but with a different permutation in general, which is I plus 4 mod 8. Okay, and again you can easily convince yourself that 0 maps to 4, 1 maps to 5, 2 maps to 6. That works for the things starting in this value. If you have 4, you add 4 to it, you get 8, which gives you 0. 5, you add 4 to it, you get 9. Mod 8 is 1. 6, you add 4 to it, is 10. Mod 8 is 2. So again, it's like it does what you expect it to do. Okay, so all right, so you have the sim operation. It's like this flip between these two things, right, in this way, and then the eNext operation, it's like has this kind of cyclic permutation. All right, so that's sort of the basic data structure we're going to work with, and then the next thing we'll talk about is how, given this particular sort of, in some sense, over-representation, it's like of the triangle, we'll then add connectivity information to this as well. Okay, so let's just stop here for now.